Thank you, Alec, and thank you, Dor, for having me out here at the Scylla conference. It's great to see everybody here in the Scylla community. I'm Jason Plurad. I'm from IBM, as we've said. I work in open technology, and I've got, I think, one of the coolest jobs out there. I get to work with the open source community and see how we can apply what's the latest, greatest things in open source and see how we can integrate it into our products and solutions. IBM is a huge company. We've got 400,000 people, so there are lots of interesting pockets within the company to work with. But as an open source advocate, I get to work with the open communities. And as you can see, I've been a PMC member and committer at Apache TinkerPop, which is a graph computing framework. So I know what you're thinking. You know, Scylla it's a column store. Why do I want to talk about graph computing? My expertise in open source is really around data. So that includes NoSQL stores, big data analytics, stream processing, and graph databases. Just quick show of hands. Who here is familiar with graph databases, graph processing? Okay, not bad. That's about 25% of the audience. So we'll talk about how when you start going into NoSQL, as you bring more and more data into your application, it's easy to see how things are connected. And the idea of using a graph becomes more and more appealing. We'll take a look through the graph landscape and the differences between a graph database and a graph processing engine for full graph analytics. And then lastly, we'll go specifically into the Titan graph database and the Scylla database and see how putting those two things together can be a multi-model type of approach into your next data application. I keep pushing the laser button. So graphs. Graphs are really nothing new. I mean, we celebrated over this past summer the 25th anniversary of the World Wide Web, which was, by and large, a huge success for graphs. Tim Berners-Lee had the idea of linking information together through HTTP. And since then, one of the biggest innovations there out of the gate was from Google. They came up with the idea of the PageRank algorithm. So rather than trying to index every single website, they took a closer look at the relationships between those websites, being able to serve to you better results by inspecting the relationships between websites and seeing which ones point to the most popular one. In 2006, Google continued the trend with releasing their big table paper, and this launched the NoSQL revolution. And now suddenly we were free of the relational database bounds, and people were starting to look at data in different ways. And around the same time, we started seeing social and open source type of coding styles to emerge in the market. So things like Facebook and Twitter, their ideas of social graph and being able to identify how people are connected. Then you start looking at internet properties like Netflix, being able to analyze your queue and your viewing habits to be able to recommend the next great thing to watch, or Amazon.com being able to recommend different products to you to buy. So by and large, graphs are just starting to eat the world. Before I joined the Open Technology Group, I worked on a product called TADM, Application Dependency Management. And it was a configuration management database. And basically, it was just trying to understand your application infrastructure. So that way, if, let's say, a web server goes down, how does that impact your business application? We're seeing that now with the mobile revolution and Internet of Things, as we see more and more internet-connected devices coming on, with smartphones in everybody's pockets, connected homes, connected automobiles. We're just going to see more and more data being brought into the fold, and graph can be at the center of that party. When we start first looking at graph computing, we did a survey of about 12 different graph databases at the time. This is around 2011. And every single one of them had pretty much the same underlying framework, which was called TinkerPop. TinkerPop was created in 2009 by Marco Rodriguez, and it was his goal to have a vendor-neutral, open-source graph computing framework. So TinkerPop provides a lot of the key pieces that you would need if you were trying to build a production-grade database. It has the core APIs for creating a graph. It has the traversal language for being able to get your data out of the graph. It provides a server, and it has 2 different abstractions for querying different types of graphs. On the left, we have the graph database, and we have a graph processor for more whole graph analytics. So seeing that graph would be really important going forward, we helped them move into the Apache Software Foundation for more legal protections and even more broader appeal. So in 2015, we took them into incubation at Apache Software. And then this past summer, we went top level. So we're now a top level project. We have about 50 contributors, and we've doubled the number of committers since we entered incubation. And we're just about to release the 3.2.2 release. And things are moving along pretty well. And we'll see that we have a rich ecosystem of providers to bring graph to you. So what is a graph? Graphs are really nothing new. Graphs, from a mathematical perspective, graph theory has been around since the 1700s with Leonard Euler's paper on the 7 bridges of Kronenberg. Graphs are real easy. I mean, they're whiteboard friendly. You have your vertex, which is your entity. These are the things in your data. And they're connected to other vertices by edges. Edges have a label associated with them and a direction. And with a property graph, you can't have a property graph without properties. So with TinkerPop, you have properties on vertices, you have properties on edges, and you have properties on properties. It really bends your mind, the different ways that you can model a graph. So now that you've got your data in a graph, to be able to get the queries, the things that you're interested in back out, we have Gremlin, which is our domain-specific language for graphs. It's modeled as a functional data flow language. It leverages Java 8 with its Lambda syntax. Out of the box, TinkerPop comes with about 30 different types of traversals to give you the rich ability to traverse through the graph in many different ways, branching, side effects, looping. And it also has a match step, which gives you more of a declarative approach to querying your graph. Also, we support other languages besides Java through the Gremlin server. We have 2 approaches for this. We have the language driver, by which you pass a string across the wire to the Gremlin server, where it gets evaluated on the JVM. And we also have something new that's coming out in just a couple weeks here once we finish the vote, which is called Gremlin language variants. The first language variant is Gremlin Python. And what that enables you is within your language of choice, which is going to be Python for right now, we have the Gremlin constructs in Python natively, so it seems more seamless and you're not parsing strings all the time. So those are some of the cool things that are going on in TinkerPop. So when you start looking at TinkerPop, TinkerPop out of the box doesn't really come with much besides the language and the server. At the end of the day, you still need an implementation. So when you start thinking about graphs, there are 2 main styles of querying against a graph. You have the whole graph type of analytics. We call that OLAP, or graph processing. That's on the right side here, where we have things like Apache Hadoop-based graph computers. Spark and Giraffe are the 2 implementations that come directly out of the TinkerPop project. You want to think about whole graph analytics when you start doing, say, queries that affect or try to find everything in a graph. So if you have, I like to tell people when you start to do graph modeling, say it in English first, because that really triggers in your head what you're trying to do. So if you wanted to say, show me the top 100 people who liked Star Wars. Even though it sounds like you're asking a small query, you're actually going through every single person in the graph to find out whether they match that criteria or not. Another use case for OLAP would be if you had an algorithm that tried to find every path, say, between A and X. I mean, there might be one shortest path between them, but once you consider all the backtracking and potential loop conditions between nodes, the number of paths can explode. So that's OLAP. On the OLTP side of the house, this is more of the real-time type of queries where you're trying to do more of a neighborhood type of query. So you start with a specific node. We like to call this like an egocentric type of query. You start at a very central node, and then you do hops out from that node. The number of hops could be a long way. It could be, say, a 10, 20 hop traversal. But the key is making sure that as you traverse out from node to node to node, that you're following a very specific path. And using your graph model with the labels and the properties, you can filter down through the graph to really narrow in on the specific thing that you're asking of your graph. Out of the box, TinkerPop comes with an in-memory graph representation called TinkerGraph, but the vendor community provides a lot of the actual OLTP databases, and some of our providers are out there with Titan, OrientDB. Stardog and BlazeGraph come more from an RDF type of background, but they still implement the TinkerPop interfaces. So for OLAP, as I mentioned out of the box, we give you a Spark graph computer and a Giraffe graph computer. Apache Spark, as you're probably aware, is probably one of the most popular Apache projects out there. I think I saw recently that 40% of the contributions at the ASF are going specifically to Spark. And for good reason. It's with its in-memory processing, it's fast. I mean, it's basically Hadoop.2. And it works out really well for whole graph analytics. Giraffe came out of Facebook, actually, and it's still out there. And in some cases, it can work out better for your graph application, especially if you have a large graph. Apache Giraffe is built on top of MapReduce, so you have that upfront cost of creating the MapReduce job. But if you have a huge graph, that upfront cost is amortized. But we can see with Apache TinkerPop, we have a common graph API. TinkerPop defines a vertex program which gets executed against the graph computer. You write that same vertex program, you can choose either Apache Spark or Apache Giraffe, and it'll run. The graph program splits up your vertex program and distributes it out to the worker nodes, so that way you can get your result in a quicker manner. So now that we've chosen either one for OLAP, we start looking at the OLTP side of the house. As you build your graph application, most people that I've seen on the TinkerPop and community, they come looking at Titan. Titan is really flexible. It comes with a pluggable backend for storage and a pluggable backend for indexing. And this gives you a lot of flexibility in terms of deciding what you're comfortable with and what you want to do. Aurelius itself, they were a graph consulting firm. They were founded probably in 2010, 2011. And they released Titan 1.0 in September 2015. Keep in mind, this is about 7 months after Aurelius was acquired by DataStax. So there really wasn't a great reason that Titan ever needed to reach 1.0 out in the open source. So it was a gift from the lead developers, Matthias and Dan, that Titan is available for the open source community to use. One point of contention, though, is that it has an Apache license, but it's not housed at the Apache Software Foundation. So what difference does this make? Well, for one, it's really confusing. There've been, if you look for Apache Titan, you'll find many people who've been confused by this distinction. But Titan is actually still owned by DataStax. So that means that their source code repository, the pull requests, and the issues are still owned by DataStax. But I'll let you know that the community is still alive. Development has slowed a bit, but DataStax has continued to allow patches to be contributed into the code base. And from the community, we have lots of great pull requests just sitting out there that if you're willing to build your Titan distribution, you can be running with the latest code base. So I think there's still a lot of potential and definitely a lot of interest with Titan. And we still use it in IBM, and I know lots of people out in the open source are using it. So data stacks, what's up with them? Over the summer, they released DataStax Enterprise Graph. It's about 15 months after they were acquired. Good news is that it's an Apache TinkerPop compliant code base for both OLTP and OLAP. But the big problem is that it's not open source. Many other pieces of their DSC infrastructure, like Solar and Cassandra, are obviously at Apache, but not the graph part. It's Titan-inspired. If you read through their marketing materials, it's Titan-inspired. So it has a lot of the same features that we see in Titan, but they've tied it directly to Cassandra and their code base, which makes sense. It also comes with some good tooling that can help you get started with Gremlin. It has syntax completion and visualizations. But it's not open source, so you don't really have the flexibility to swap out the back end. Say if Cassandra isn't working for you, you can't try out HBase or DynamoDB, for example. So now let's take a closer look at what's going on with Titan and Scylla. Titan itself started in 2012. The Aurelius guys had established a partnership with Pearson Education, and their goal was to educate the planet. They were rolling out some MOOCs, massive open online courses for bringing learning materials out to the masses. And what they were noticing was that by analyzing the graph between the teachers, the courses, and the students, and especially the discussions between the students, using a graph database gave them the opportunity to really understand how people are learning, and they saw great synergy in that. So their requirements were being able to support both OLTP and OLAP, and really to have an open source offering. Back in 2012, there was no such thing, so that was the essence of Titan. So with Titan, we have several important features. So at the very first, we have data management. Data management comes down to how do you get a graph model stored into another store, a column store, whether it's HBase or Cassandra. What's important here is that Titan stores data as an adjacency list. So your row key is your vertex ID, and then all the other columns include your properties and the incident edges. What this does is this gives you index-free adjacency. This allows you to jump from one node to another without having to do a massive join between two huge tables. Along those same lines, with Titan, the idea is that you define a schema, a graph schema up front, and this allows Titan to understand your data model, so that way it can more intelligently index and align your storage, so that way you're able to get your data out more efficiently. Vertex-centric indices, this is a problem that you'll eventually run into as you start working with graph databases. This is I used to call it the Justin Bieber problem, but this is now the Katy Perry problem. If you're looking at your Twitter graph, Katy Perry is the most followed person out there with over 9 million people. As you have a graph, you'll notice that there are a few select nodes that were massively more connected than the rest. And if you ever try to traverse through one of them, well, you could potentially be traversing through millions and millions of different edges. The approach with vertex-centric indexes is that it gives Titan the ability to more intelligently sort and filter through the edges by creating an index from the view of a vertex. And then by sorting the edges based on the label and some other attributes that you've defined, you're able to more selectively decide how to traverse through that supernode. Then with graph partitioning, this is another key piece as your data size increases. Titan has two types of partitioning. It has the idea of an edge cut. So this would be if you have a large graph and you imagine it spread out on a table. For example, if you wanted to separate by geography. So if you had a geographically dispersed graph, you'd probably find that most of your connections in North America are more likely to communicate or be connected with other nodes in North America, whereas the ones in Asia and Africa are more connected there. So by cutting along those edges, you can partition your data that way and separate your data. The other idea is there's the idea of vertex cutting. And this is how we separate out the supernodes, the Katy Perrys of the world. Essentially, what you end up doing is you replicate that vertex into each partition. So that way, say, Katy's followers in North America are separate from her followers in Asia. And you can go out there for more information. This is a big block diagram of Titan's architecture. So at the top, that's your graph application. We can see that it's enabled by TinkerPop, both on the OLTP and OLAP side. TinkerPop has the core graph APIs and the query language. These three blue layers here, I can use this. These are your key Titan layers for managing your graph data into the backend stores. Key piece here is the transaction layer. When you're dealing with a graph, your idea of a transaction is a little bit different than the backing store. So when you're building a graph, your idea of a transaction is, I added these 10 nodes and these 5 edges between them. And the idea from a graph perspective is that your transaction might actually end up being multiple transactions, both to the storage and the indexing backends. So Titan has the means to encapsulate all of that. On the OLAP side of the house, as I discussed before, a lot of those are coming out of TinkerPop with the graph computers for Giraffe and Spark. The key piece out of Titan is a Titan input format, and this allows it to efficiently move the data out of your graph stores and into HDFS. Along the bottom here, on the close end, we have the external indices. This is for full text search. It uses Elasticsearch and Solr and Lucene. Those are your pluggable options. You can just drop one in and use whatever you want. Then for storage backends, out of the box, there's support for Cassandra, HBase, and Berkeley, and that little guy. One key thing to note here is that most of these projects are hosted at the Apache Software Foundation. So Spark, Giraffe, Hadoop, TinkerPop, Cassandra, HBase. It's a full house. So why would you use Scylla? Well, it's a drop-in replacement for Cassandra, and it's built on Cassandra 2.18. And that was pretty much the version that was available when Titan 1.0 was released. So in December this past year, my fellow PMC member over at TinkerPop, Ted Wilmes, he attempted to just go ahead and copy a key space over from Cassandra and use Scylla. And he immediately ran into unsupported exceptions with Thrift. Titan is built on Thrift, so it hasn't moved over to CQL yet. But over the summer, things started to move in Scylla, and all of a sudden we had Thrift support. So in July, I started going ahead and testing it against Thrift, and well, it started to work. Everything wasn't perfect, but Scylla is it's an open source company, and luckily for me, Duarte Nunes out there, he was very responsive on the issues tracker, and we worked through probably 2 or 3 different bugs that were affecting the implementation of Titan with Thrift, and it works. I can tell you right now, I tested OLTP and OLAP with Titan, and it works with Scylla 1.3, which was just released a couple days ago. And it's fantastic. So what I see here is that the interest in Scylla has now reawakened the slumbering giant that was Titan. People are really getting more excited about what can happen here in the open source community, especially in graphs. So what are the next steps we need to take? Well, step 1 is we need to start benchmarking our graphs, both on the OLTP side and the OLAP sides of the house. Right now, there isn't a great story for benchmarking with graphs. Most of the graph benchmarks are more OLAP focused, and they come more from an RDF type of background. But for Titan, which supports both, we need to look at both sides, especially as we try to compare Scylla versus Cassandra versus HBase, and do more of an apples-to-apples comparison. Next, Titan, its backend for Cassandra needs to be rewritten. Thrift is going out of support in Apache Cassandra 4.0. It's been pretty stable for several years, but they said it's going away. So this is essentially a rewrite. And DataStax has already done it with DSE Graph. But we have the opportunity in open source to go ahead and do this too with Scylla. We can take advantage of new features coming down the pipe, like materialized views when those come in. I think it's Scylla 1.5, I think I saw on the roadmap. So there's great potential there to contribute to Titan. Then some other ideas, native search. I don't know whether this would be using something like the SASE support, the SS attached storage indexes from Cassandra, or maybe this is something more along the lines of Alessandra, where Scylla perhaps implements the Elasticsearch APIs. But getting that native search plugged in with Titan, I think that could really create a new interesting story and some huge performance gains for Titan and graph computing. So my company, IBM, we have this mantra called open by design. And it's basically like I told you. We look out to the open source and we partner with open source to really take advantage of the greatest stuff that's out there. When you go proprietary, you've closed off the whole world of developers that are out there. Maybe in IBM we can get away with it. We've got 400,000 people, but we choose to embrace the open community. And Scylla is the same way. They have their legacy coming out of the KVM hypervisor, and they've distributed their developers all over the world. I think it was 30 different sites, something like that. So they understand the idea of open by design. By working together in open communities, I think together we can all push the industry forward. Now, even though you have an open source core, it doesn't mean that there isn't a way for you to benefit as a company. At IBM, we have two offerings here that I'll mention. We have IBM Graph, which is a hosted, managed graph database as a service. As you saw before, there's a huge stack of software running under the covers. And on top of that, you're still trying to build your application using a graph. So if you leave the management and operations of your graph database to us, it's for you. Out of the box, you get 30-day free registration and free trial. Go ahead and try it. Go to ibm.biz/IBM Graph. And then, as Nick stated before, IBM Compose is rolling out a Scylla beta. If you send an email out to scylla@compose.io, you can go ahead and try it out. And I think at the end of the day, partnering with open source is the way to go. And if you're interested in contributing to either Apache TinkerPop or Titan, reach out to me, and I'd be happy to help you out and help you join our open source communities. Thank you.